lecture. So if you, for some reason, are sick or flat tire, whatever, you can access my lectures at any time, okay? I do still recommend that you come to class because we do a lot of in-class activities that will really help you for the upcoming exams, okay? Any questions so far? Any burning questions about today's lecture? All right, so what we're going to do then is start off with the top hat question, as promised. This is just going to be a little bit of a review of what we've already done. Let's see here. Okay, oh, it's right in front of me. Oh my gosh. All right. So the first question for today, pretty easy. True or false, like charges attract and unlike charges repel? Is this true or false? Like charges attract and unlike charges repel. Pretty easy starting off. All right. We're already up to about 43 students. I think we have almost 70 students in the lab now. So I think I'm going to give you about 10 more seconds. Anybody in this room need a little time? Okay, no worries. Just give me a thumbs up when you've got it. You having connectivity issues or? Okay. I'll give you about 5 more seconds and then you and I can talk after class and get that settled. Anyone else need, you're okay? Okay, all right. Okay, so I'm gonna go ahead and close this one. And of course, the correct response is false. Good job, everyone. All right, so let's go to the next one. The next one is, as the distance of separation between charges increases, electrical force A increases, B decreases, C stays the same. So if you remember last time, this has everything to do with Coulomb's law. Coulomb's law. And this is just participation, so if you need to talk to your neighbor, that's fine, right? You want to just verify what you think is the correct answer, just turn to your neighbor. Do you think this is right? As the distance of separation between charges increases, electrical force A increases, B decreases, or C stays the same. All right, we're at 39, 40. Last time we got 45. So I'll give you about 10 more seconds. All right, we're up to 46 now. All right, how many need a little more time? Just raise your hand. All right, so the correct answer is decreases, right? It's going to have an inverse relationship. Perfect. All right, this is the last one today. And the question is, true or false? Typically, all cells at rest have a resting membrane potential between plus 20 and plus 75 millivolts. All cells have a resting membrane potential between plus 20 and plus 75 millivolts. Is this A, true, or B, false? And these are pretty typical for exam questions. Right before the exam, I'll open up all these top hat questions again with the answers so you can review them. we're already up to 43 answers. Great. Again, you can talk to your neighbors, no problem. All right, we're up to 48 now, 49. It looks like I will probably take this one for points. Okay, this is the one I'm going to take for points this week. So, did everyone have a chance to answer? Okay. If you're still having trouble, we're going to talk about it after class. All right. Okay. Let's go ahead and close this one. And of course, this one is false. All right. So what should it be? Yes, negative, I would say, yeah, right? We've been talking about it in class as negative 70 millivolts. Perfect. If you look at all the different cell types, they usually range from minus 100. Muscle cells are usually very hyperpolarized, meaning they're very negative at minus 100. Red blood cells are more depolarized, that means more positive, at minus 20 millivolts. So I would say the range is usually minus 100 to minus 20 millivolts, usually very negative. All right, thank you for participating, everyone. Like I said, I will take that last one for points. And what we're going to do is we are going to continue on about equilibrium potential. And then today's lecture, what we're going to do is we're going to talk about Ohm's law one more time. I have to roll out all the variables when it comes to the electrical components, okay? And I'll go through that slowly. I'll give you some visuals as to how to remember Ohm's law in electrical terms. And then we're going to jump right into we're going to dive right in to understanding the resting membrane potential today. Okay, so first I'm just going to ask the question, how many of you are still a little fuzzy about what the equilibrium potential is? Okay, fair enough. I really appreciate your honesty because that helps me actually go back and talk about it. All right, so what I'm going to do, let's just do a little chalk talk then. Let's just review for a minute. Okay. Now, we've talked about a typical cell having concentration gradients that have been established by what? Do you all remember why sodium is very high on the outside and low on the inside? So the bigger the letters, the higher the concentration. Okay, so the concentration gradient looks like this. Why is that? Why? Yes. That's right. It's the sodium-potassium ATPase. It actually uses ATP to pump 3 sodium out of the cell. So for every turn of the pump, 3 sodium ions are forced out, 2 potassium ions are forced in. And it uses ATP, the energy from the hydrolysis of ATP, to basically move these molecules against their concentration gradient. Okay? So, the equilibrium potential is this. When you take a look at this, we already understand what the concentration gradient or chemical force is. We've talked about it as a statistical force. So, if you're only looking at the chemical force, the tendency is for sodium to move into the cell, just because of probability statistics, okay? All right, then we added on, right? Like Pilates. We added on. Okay, so what would it take? What would the membrane potential have to be? Remember, that is the membrane potential we've already said at rest is pretty negative inside the cell, right in that inner leaflet. So when we measure it with a voltmeter, that's what it's going to be. It's going to be relatively negative right in that inner leaflet compared to the back, which we set at 0. Okay? So this is a potential difference. What would this have to be? What would the membrane voltage have to be in order to prevent sodium from coming into the cell? Does anyone remember from last time? we drew our graph here, what would that voltage have to be? It would have to be positive, right? So think about it this way. I know this is a little bit confusing, but this membrane potential would have to be pretty positive. I'll draw it out here to repel sodium so that it doesn't enter into the cell, right? Because like charges are going to repel. So that voltage would have to be pretty positive, right, compared to 0. We actually calculated it out at one point, and we said it would, in our one case, let's just make it up, 61 millivolts. So the inside of the cell would have to be pretty positive, right, in order to prevent that net movement of sodium into the cell, okay? All right, so the equilibrium potential is that exact voltage, right? That exact voltage. It's a calculated value. We didn't measure it, but we did calculate the exact voltage that would have to exist in order to prevent the net movement of sodium down its concentration gradient into the cell. And at that exact voltage, that's where the electrical work and the chemical work are equal but opposite in magnitude. Okay? Or equal in magnitude but opposite in direction. Should be more clear about that. Equal in magnitude and opposite in direction. What is this called? This is a good definition that may be on your test. Electrochemical equilibrium. When the electrical work equals the chemical work, this is electrochemical equilibrium. And let's take a look at our slide. This is kind of where we left off. Right? So, we had already defined the electrical work as ZFE. That's the electrical work, or WE. And we defined the chemical work, RT, times the natural log of the concentration gradient. Multiply that together, okay? So this is where the electrical work exactly equals the chemical work. We're at electrochemical equilibrium. We just rearranged the statement, and now we're going to solve for E, which is called the equilibrium potential. This is the voltage in which the electrical work and the chemical work are exactly balanced. Okay? So you're probably wondering, why do I have to know this? Right? I promise it'll all become very clear, especially when we talk about action potentials. You're going to be really happy that you learned about equilibrium potentials. Okay? All right. So, is that still okay? Do you still feel like it's still a little fuzzy, but I'm sure when you run the numbers again, we'll kind of try to figure it out. Okay? Ask questions as they come.
So
Yeah.
you're talking about which direction the ions
That's
will come
right.
out of the cell.
That's right.
So anything that's above the RMP, the resting membrane potential, if it's above it, it's going to be going out of the cell. Is that
Yeah.
true?
Okay, so let's take it from the top. It's a great question. All right. So for those that are just coming into the class, I use a dashed line here because it's just a theoretical value. Okay? It's just a calculated value. I haven't measured anything. What if the resting membrane potential is plus 61 millivolts? Which way would sodium be moving in the cell? If the resting membrane potential was plus 61 millivolts,
It would be moving.
there would be no net movement. No net movement. Okay? So if I had the resting membrane potential, not right, it was sitting right on top of the equilibrium potential, there would be no net movement. All right? But that's not usually the case. Okay? So, usually the case is, we'll keep the equilibrium potential right there. The resting membrane potential, as we just talked about, minus 70 millivolts. All right, how do you decide which way the ion is moving? Always use this as your reference. Ask yourself, where does the resting membrane potential sit? Is it more negative? Okay, so this is membrane voltage in millivolts. Okay, and ask yourself, where does the actual membrane voltage that I've measured with a voltmeter, where does it sit? Is it more negative or more positive? It's more negative, right? So I always like to draw a cell with this as well, right? When you have your scrap piece of paper during the exam, draw your cell out. Sodium is a positive ion. I just put a little negative sign here because that, just in my mind, tells me that the resting membrane potential is more negative. That's not an actual value. Okay? These two are going to attract, and sodium is going to move down its concentration gradient into the cell. Okay? Anything below this line, sodium is going to be moving into the cell. Okay. Here's how I really want you to think about it. In this case, the chemical work is greater than the electrical work. That's how I really want you to think about it. So it's going to proceed, it's going to continue to move down its concentration gradient. Another way to say this is the electrical work is not sufficient enough to prevent the net movement of sodium down its concentration gradient. Does that make more sense too? Okay, let's try it the other way. Let's say that under experimental conditions, or if you open up a calcium channel, the resting membrane potential is plus 100 millivolts. Okay? Now think about it. Here's your reference. This is where there's no net movement. Where does our resting membrane potential sit relative to our reference now? It's more positive, right? More positive. Way more positive. Really positive. Sodium's a positive ion. Now it's actually going to start to push sodium out of the cell in the face of a huge concentration gradient. It's going to be going against its concentration gradient. In this case, the electrical work now is so great that it's starting to push sodium out of the cell against its concentration gradient. Now this equilibrium potential is probably now starting to become even more clear. It's still fuzzy, but now you can see the beauty of this particular value and how to think about it. Pretty good? All right. So now on your sheet, you should be able to calculate all the equilibrium potentials and predict which way the ions are moving. Sometimes when you get home, it's still a little fuzzy, but I'm telling you now, it's about practice, 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 practice. And the second problem set is almost exactly like the first one. For problem set number 2, there's a part 1 and a part 2. They're almost identical, but it's just to give you more and more and more practice. So a lot of times, in the past semesters, students have said, can you give me more problems just to practice? And that's why there's a part 2. Okay? Any questions? Yes?
Wait, so you said that when the cation moves in, the electrical work is not sufficient enough, but then the electrical force is also greater than the chemical force?
No. Okay, so I hear what you're saying. So when sodium is moving in with its concentration gradient, then the chemical work is greater than the electrical work. Okay? However, if the inside of the cell, the membrane potential, has such a positive value, plus 100 millivolts, now sodium is moving out. In this case, now the electrical work is greater than the chemical work. And now the electrical work is actually pushing sodium out of the cell in the face of a huge concentration gradient. Okay? Thank you for that clarification. Yes?
So in the case of an anion instead of sodium, would it just, if it's greater than the, if you're still giving it 61 millivolts as the equilibrium potential, it would just be flipped?
Yeah, exactly. Okay, so let's take, usually the equilibrium potential for potassium is fairly negative because the concentration gradients are opposite. High potassium inside, low potassium outside. So that, when you run the numbers, that gives you a very negative equilibrium potential for potassium. But, right, the directions are still the same. Out, in, right? So you're right. When you look at, if the resting membrane potential sat right on top of the equilibrium potential for potassium, there would be no net movement. If it was more negative, then potassium would be moving in against a large concentration gradient. And if the resting membrane potential was more positive, then it would be moving out with its concentration gradient. Okay? But your question was, what happens with anions? They are flipped. You're absolutely right. Okay, so then it would be out. In. Does that make sense? Okay, so I can see that the wheels are turning. I can see that you're starting to really put the pieces together, and I really appreciate that. Okay? All right, so this was a great review. This isn't easy stuff. This is a very wordy slide. Let's see here. Here's where I want to go. Now, I'm actually really sad about this. This was a great computer simulation about 10 years ago. And then the professor must have retired and he didn't maintain the site. And it just kind of fell apart. Like my computer couldn't see the computer simulation anymore. So I did record it about 3 years ago. It's a little bit glitchy, but we're going to go through it again, okay? And I apologize for any kind of delay. It's not as smooth as I'd like, but it's still a great illustration. First of all, this is very wordy, but it is kind of how to predict which way the ions are moving. So if you get home, I mean, we've already gone through it in class, if you get home and you need some text or instruction, this is what that slide is all about. Now, how many of you remember this particular slide? We talked about this in the very beginning. We actually talked about diffusion and diffusional equilibrium, okay? And we actually saw that basically what this is 3 different time points where molecules are moving from one compartment into the other until diffusional equilibrium occurs, right? And we said that change in concentration could be depicted as basically an exponential function of time, right? Okay, so you can commit, and I said commit this one to memory. All right, so let's take a look. Now you can actually see fusion of charged particles and the diffusion of uncharged particles first, and then the diffusion of charged particles. So this is on your website. Okay, so this is under the diffusion of charged particles. And again, if you look at each one of these sections, you'll find the recorded lecture. So after today, it'll be either in this section or Ohm's Law section. Okay, so the recorded lectures every time are posted. Here is our membrane simulation here. I played it this morning, and so I have to go. I might have to go back, sorry. I told you it was like being in the gym. Okay, let me just refresh this. Maybe that'll help. All right. So, yes, that did help. Okay, so at the very bottom here, I'm not going to turn on the, great, it's running. Okay, so I'm not going to turn on the sound. I'm just going to walk you through it. But I believe I actually recorded an audio over it too, so if you need some context, you can just listen to this again. All right, so this is a computer simulation called membrane. And we have two compartments here. We actually have an outside compartment and an inside compartment. I'll follow my arrow. The volume is going to be a finite volume, not infinite. And we're going to start with uncharged particles. Okay? Inside has a concentration of about 200 millimoles. Outside has a concentration of only 20 millimoles. Okay? So this is almost like potassium, high on the inside, low on the outside. All right? So what we're going to do is we're actually going to open up a channel, and you can see in real time the influx and the outflux. The influx is in yellow there, and the outflux is in green. And that's going to be the unidirectional flow for influx from the inside, or I'm sorry, from the outside to the inside, and then the outflux is going to be from the inside to the outside. Okay, so when I open up this channel, you'll be able to see diffusion in real time of uncharged particles. Okay? Any questions so far? I just have to wait until it gets there. Okay, there it goes. I opened up that channel. I started the program, and then I opened up the channel. And then you can see in real time the outflux and the influx. Okay, it's going to bounce around, right, until we reach diffusional equilibrium. All right, remember this is uncharged particles. And this will continue to bounce around. You can actually kind of see the actual concentrations. If we plot this over time, this is what it looks like. Just like the graph that I showed you before. The change in concentration is going to be depicted by an exponential function of time. Just like the graph that I showed you before. Now it'll bounce around, but we've basically reached diffusional equilibrium. Pretty good? All right. All right, so now we're going to go back. We're going to change the parameters. Okay, and we're still going to use a finite volume. You had to stop the program and start it back up. But instead of uncharged particles, we're going to click on cations. And now it's going to be charged particles. Okay? Now, notice that with a charged particle, now you see the membrane voltage at the top. Remember, with the charged particles, if there are ions moving across the membrane, you are going to have a membrane voltage. All right. In this case, there's no channel that's open, no ions are moving across the membrane, so the membrane voltage is 0. Okay? And you can see the concentration inside and the concentration outside, just like before, influx and efflux, right? And this is very much like potassium inside the cell. Only one ion is moving across the membrane. You can actually calculate the equilibrium potential, and that would actually be the resting membrane potential. I'll show you why in just a little bit. Okay, so only one ion can move across the membrane, and the equilibrium potential should be the resting membrane potential. You could calculate it out right now because you know how to calculate equilibrium potential. For potassium, it should be pretty negative, around -60, if you actually ran the numbers. Okay? So I'm going to go ahead and open up this channel. And you can see the voltage is already starting to change, becoming more and more negative. You can also see the blue and the red ions lining up at the membrane. Remember, the membrane is acting as a capacitor. It has the ability to store charge. Voltage is bouncing around about -60 millivolts, like I said before. Okay, perfect. That's It's what we would have predicted with the equilibrium potential. Now when we plot this, you're going to be amazed. Concentrations aren't changing. All right, why? Because almost immediately the electrical work and the chemical work become equal to each other. So there's no concentration changes. There's no net diffusion, right? Pretty cool, pretty cool. All right, so that's something to commit to memory. All right, that's my computer simulation. Love it. I was so sad when it didn't work anymore, but I did capture it. Okay, any questions about that? All right, so here is the biological significance, okay? I want you to think about this when we get to neurons. All right, when we get to neurons, the resting membrane potential stays pretty steady until all of a sudden these voltage-gated sodium channels open and it pulls the membrane voltage towards the equilibrium potential. Okay? Then sodium closes, these sodium channels close, potassium channels open, pulls the membrane potential towards the equilibrium potential for potassium, and then it goes back to rest. It's not about concentration changes. The concentration doesn't change, right? So the pump isn't working overtime to reestablish those gradients because hardly any ions have to move across the membrane for you to get these sweeping changes in membrane voltage, okay? So not many ions have to move across the membrane for you to get these sweeping changes in membrane voltage. It's just about conductance changes. It's just about the opening and closing of channels that elicits these action potentials. They're beautiful. Again, if this doesn't resonate yet, we're going to go over it again even more slowly when we get to action potentials, okay? But that's where we're going with all that. That's why we need to know these components, okay? All right, so let's fill in some blanks. I realize I just said a mouthful, and you're probably like, I didn't catch that last part. Okay, I get that. I get it. So let's fill in some of these blanks. Now some new material. We're going to actually go through Ohm's law. We talked about Ohm's law on the very first day. And then we're actually going to go through the resting membrane potential and then the contributions of conductance and driving force to the resting membrane potential. So this is where we're going today. All right, again, these are pretty easy learning objectives. Understand Ohm's law. Know the definitions of current, voltage, resistance, and conductance. So this is Ohm's law in electrical terms, and I'm going to walk you through it pretty easily. We'll talk about it in hydraulic terms just to help you kind of visualize what's happening. All right, we'll come back to this diagram. This is just going to help us. You probably already can see how to calculate. You already know how to calculate the equilibrium potential. 1C on your problem set was to actually draw a graph just like this, right? And then you can see the actual resting membrane potential that's measured by a voltmeter, in this case is -70. All right, so let's talk about Ohm's law in electrical terms. Current is the same thing as flux, what we talked about in chemical terms, or flow, like when we think about a garden hose physiology, or blood flow or airflow. That's going to be mils per minute. So current is a flow. Current is a flow of charge. Coulombs is a unit of charge per second, per unit time. So think about it as a flow of charge. The driving force is our membrane voltage difference. Okay, so it's actually going to be the membrane voltage minus the equilibrium potential. That's our driving force. I'll talk about that in just a second. And resistance is conductivity. You all know, you have some physical intuition about it, right? Copper wires are very conductive. They have a high conductivity. Rubber is terrible, has a very low conductivity, right? That's what we're talking about here. Conductivity is the inverse of resistivity. So copper has a high conductivity, it has a very low resistivity because it's just the inverse of resistivity. Conductivity equals 1 over resistivity. Okay. Oh, how did that happen? That was weird. Okay. And then the diameter of the conductor. The larger the diameter, the greater the conductance. All right, so I want you to remember what we talked about last time too with our example. Poor Julius Bernstein, 1902, really struggled with the resting membrane potential. Like I said, I could imagine him like banging on that voltmeter. Like, why isn't it the same as the equilibrium potential for potassium? Okay, he didn't realize that there were other ions moving across the membrane. Okay, so we're going to revisit Bernstein's hypothesis. I want you to know that he really did capture the essence of the resting membrane potential, though. Also, understand the differences between equilibrium and steady state, as we talked about last time. And then know the meaning of the constant field equation. This is also called the Goldman-Hodgkin-Katz. Okay, so I know a lot of other physiology courses just kind of roll this out and they don't really give you any context with it. They just say, it's in your textbook, right? Know it. But I really want to give you some context here. So we're going to go through that in a little bit kind of systematically. Okay, so let's talk about first the constant field equation, or what's known as Goldman-Hodgkin-Katz, or GHK. All right, with this equation, you can actually predict the membrane voltage, the resting membrane potential. You can predict it. Now, you already know you can measure it with a voltmeter, but you may not have known that you can predict it by using this equation. Here's the take-home message for you all, okay? Every ion moving across the membrane plays a role in setting the resting membrane potential. Every single ion moving across the membrane plays a role in setting the membrane potential. Okay? So this is an incomplete equation. This only has 3 ions, potassium, sodium, and chloride. But you can imagine all of the ions moving across the membrane play a role. Magnesium, calcium, right? So just know that this is incomplete. Now, this also uses permeability terms. Permeability you can think of as a pathway for ions to move across the membrane. That's an okay way to think about it. Some people say conductance. Conductance is basically a pathway completely through the plasma membrane, right? So you can think about both of them as pathways. But I'm here to tell you, we'll revisit this as well. Permeability and conductance are not the same terms. They are not the same, even though they almost sound the same. There's a great paper by Dave Dawson who used thiocyanate to distinguish between permeability and conductance. So here's what I'm going to say. Permeability is the ease at which an ion enters into the plasma membrane, enters into the pore. Conductance is the ease at which an ion moves all the way across the membrane into the cell. A little bit of a distinction there. They sound the same, but they are different, and experimentally you can dissect them out. So permeability, again, is the ease at which it enters into the outer leaflet, into the plasma membrane, the inner part of the plasma membrane into the pore. It's just like entering into the pore. Conductance is the ease at which an ion moves all the way across the membrane into the cell. Permeability is very hard to measure in the laboratory, but conductance is really easy. Okay, so we're going to use the chord conductance equation, but these are very similar terms. Wow, this just keeps advancing and I'm not doing anything. Static, I guess. All right, so this is the Goldman-Hodgkin-Katz, right? We're going to start off with this one. If I set the permeability for sodium and the permeability for chloride to 0, so the only ion moving across the membrane is potassium, what does this equation look like? If we set sodium and chloride to 0 and all the other ions to 0, they're not moving across the membrane at all. Only potassium is moving across the membrane. What does this look like to you?
Equilibrium potential.
It's the equilibrium potential. So if there's only one ion moving across the membrane, the actual membrane voltage is going to be the equilibrium potential. Okay? Bernstein almost got it right? He was really close. He was really close. He captured the essence. He didn't realize that really 90% of the total conductance was due to potassium. There were still other ions that were moving across the membrane that were pulling the membrane voltage away from the equilibrium potential for potassium. So, almost right? Okay. So, instead of using Goldman-Hodgkin-Katz, again, it's very hard to measure permeability in the laboratory. I know a lot of instructors don't roll out this chord conductance equation, but I just really feel it's a lot easier to use. Okay? So this states that the actual membrane voltage, you can predict it with this equation. Remember, the membrane voltage you can measure with a voltmeter, but you can actually predict it with this equation. Uses conductance. So G is conductance. Okay, G is conductance, GT is total conductance. And then you multiply that by the equilibrium potential for sodium. So it's the percentage of the conductance that's due to sodium moving across the membrane. And then with potassium, and now this is just a 2-ion system. All right, so we're only, for simplicity's sake, we're only using sodium and potassium, but there's lots of other ions that have to be incorporated. But for our purposes, the total conductance is only due to sodium and potassium. Okay? Now, in this case, we can actually predict the membrane voltage. All right, we're going to come back to this. I've been using terms like conductance, permeability, but I need to go back and talk about Ohm's law. Okay. For some reason, my slides keep advancing. Tell me if the slide advances, but this is what we're going to stick to for just a second. I've been using the term conductance with the units G here, but let's go into a little bit more detail about what Ohm's law is, just so that you can also kind of put everything together. I started off, in one of the first classes talking about Ohm's law in terms of garden hose physiology, right? So, the driving force for a garden hose is going to be the pressure gradient. Water is always going to flow from high pressure to low pressure. That's the driving force. The flow is the water moving through the garden hose in mils per minute. And then resistance would be like kinking that hose and making it hard for basically that water to get out the back end. So pressure is going to go up. Upstream from that kink, it's going to go down. Downstream from that. Okay, that's a good example of resistance. Now we need to think about it in terms of basically electrical terms. Current, again, is that net flow of charge. 1 amp is equal to 1 coulomb per second. Okay, and the coulomb is the amount of charge on a mole of any monovalent or a divalent, like calcium, is going to have 2 charges associated with it. So again, this is the net flow of charge. And it can be in amps. Voltage is the driving force. Voltage is the driving force. So voltage is measured in volts, and it's the work needed to move a unit of test charge in a frictionless manner from one point to the next. We already talked about this when we started doing our problem set. 1 volt is equal to joules per coulomb. 1 joules per coulomb. Okay? Now, 1 joule is a unit of work. It's the amount of work required to move a coulomb of charge across a 1 volt potential difference. Now, for your purposes, the driving force here is going to be the actual membrane voltage. You can either measure it with a voltmeter or you can predict it with the chord conductance equation, minus the equilibrium potential for that ion. That's your driving force. That's your potential difference. Just like our pressure difference that we talked about with the flow of water, this is the driving force for the movement of charge. Your net driving force. Okay, so it says here, in other words, it's the push or pull of an ion. It's a push or pull of what an ion experiences in an electrical field. So remember when I was talking about Einstein's relation and how he turned diffusion on its head by thinking about diffusion like a little hopping fleas, right? Electrodiffusion is like hopping fleas in the wind. Okay? Hopping fleas in the wind. The wind is the electrical force. So that's one way you can think about it. The driving force is the push or the pull that an ion experiences in an electrical field. That's the driving force, the push or the pull that an ion experiences in an electrical field. All right, so what is resistance? I put it in these terms so it's very easy to understand. Resistance is just the difficulty in which an ion moves across the membrane. If it's very difficult for an ion to move across the membrane, channels are closed, electrical fields are in place. If it's very difficult, then it has a high resistance. Okay? Conductance is just the inverse. Okay, so you can actually see here, conductance is just the inverse, 1 over R of resistance. So, if you think about it in just simple terms, conductance is the ease at which ions move across the membrane. Pretty good? Pretty good? All right, so that's Ohm's law. So we still have a lot of time here. What I would like to do is let's do a workshop now. I think that I've lectured to you quite enough. Let's actually do some of the problems on here. You should now be able to do all of the problems on all of the problem sets. Let's just first together, let's see. I don't see this on here. Let me pull up, let's see. Let me pull up problem set number. Are you asking about NaCl? And okay, this is a really good question. I had this question, someone else asked the same question after class. When you're looking at problem set, you have it in front of you, problem set number 2, part 1. I just want to read number 2. An epithelial cell is bathed in saline solution that contains 140 millimolar sodium chloride, right? What is the concentration of sodium ions in that solution? It's the same, right? because we're assuming that they're going to dissociate completely. But once you drop it in solution, 140 millimolar sodium chloride, it's going to form 140 millimolar sodium ions and 140 millimolar chloride ions. Okay, so they're going to be 2 osmoles, if you remember when we talked about osmolarity. Okay, that's a great question. Just want to clarify. I wrote it that way so that you would have to grapple with that a little bit. Okay, so let's go to our home page here. And I'm going to open up the second problem set. If you haven't found the problem sets, they're here at the bottom. And you have both problem set 1 and 2. And these are actually due February 6th, which is next Thursday. So you have plenty of time to finish it up. I will turn back problem set number 1. I thought that it might be better if I put them in alphabetical order before I just set them on the table. All right. So, let's see here. Here's a typical question that you may get. All right, so if you take a look at this, can everyone read this one? In this scenario, you're going to have to calculate the actual membrane voltage. I'm not going to say the measured membrane voltage is minus 65. You're going to have to calculate or predict the actual membrane voltage using the chord conductance equation. Okay, so let's just draw that out. This is very much like what you would see on an exam. And then we're going to play a little mind game again. All right. So in this case, this actually says, well, let's just do the whole thing, actually. Gives us a little practice. This is number 3 on problem set number 2, part 2. All right, let's calculate the equilibrium potentials for both sodium and potassium. So what we have here is sodium has a concentration inside of 4 millimolar, outside 130 millimolar. Potassium inside is 90 millimolar, outside is 5 millimolar. So you have to calculate the equilibrium potential for both sodium and potassium. You can also turn to your neighbor. You can work together, perfectly fine. The temperature is 25 degrees Celsius. Remember, you have to convert that to Kelvin. Can everybody see this okay? I know it's kind of, I wanted to keep this up, but still be able to write on the board. All right, everyone, let's just go through sodium together. There's some people that are here for the first time, so I want to make sure that they know how to work this problem. 8.3 is R, joules per mole Kelvin. What did you get for the temperature in Kelvin? It's 25 degrees Celsius, 298, right? You have to add 273 to 25. So we get 298 Kelvin. What did you get for the Z value? Plus 1, right? Plus 1. Multiply that by Faraday's constant, 96,500 coulombs per mole, natural log of 130 over 4. So what we're going to have is when we millimole are going to cancel out, Kelvin are also going to cancel out, moles as well. We're going to be left with joules per coulomb, which we already know is a volt. What do we get?
89 millivolts.
89 millivolts. Plus 89 millivolts. Perfect. It's pretty depolarized, actually. All right, so let's start drawing our graph, right? That's important. 0 millivolts. I'll turn that off when I make a point here. Equilibrium potential for sodium is plus 89 millivolts. Okay, it's way up here, very depolarized. All right, so let's do potassium. We can actually just kind of substitute this out. Potassium, same value, same temperature. Z is still plus 1. No? Calcium is plus 2. But potassium is still plus 1. Pretty good? Okay, so all of this is the same, but our concentration gradient is flipped. So it's going to be 5 over 90. Okay? Again, this is actually going to be in volts, and you're going to have to convert it to millivolts just by multiplying by 1,000. So in this case, what do you get? It's not plus 89.
Negative 74 millivolts.
Negative 74 millivolts. So just so you know, when you're doing these calculations, this should be becoming, routine. And if you get a value of plus 590 millivolts, you're going to be like, oh, I did something wrong. Okay? So minus 74 millivolts is the equilibrium potential for potassium. Okay? All right, remember these are dashed values because these are calculated values, just theoretical values. All right, so you have to do C before you do B because you don't know what the actual membrane voltage is, right? You don't know what it is. You haven't calculated it yet. I didn't give it to you. So if I said measured membrane voltage, then you knew that I actually used a voltmeter and I measured it, and that would be a solid line. In this case, we're going to predict the membrane voltage using the chord conductance equation. So let me just write this down. So the conductance for sodium over the total conductance is 5%. And the conductance for potassium over the total conductance is 95%. So that would be 0.95. Okay? So now let me just turn this off. It'll be easier for you to see. Bring this all the way up. We all on the same page? Okay, so here's how you would use the chord conductance equation. You can predict the membrane voltage, and at rest, let me just put some pieces together. This would be the resting membrane potential when the cell is at rest. is going to be equal to the conductance for sodium over the total conductance, multiply that by the equilibrium potential for sodium, plus the conductance for potassium over the total conductance, multiply that by the equilibrium potential for potassium. And just for reference to, on any question, I will make sure that this says like plus or 2 plus if it's calcium, so you don't have to guess, okay? I don't expect you to know that. I'll have that in the question, okay? All right, so let's figure this out. For sodium, it accounts for only 5% of the total conductance. So this would be 0.05 times plus 89 millivolts. Plus 0.95 times minus 74 millivolts. Okay, anybody, can someone give me that number?
Negative 65.85 millivolts.
Okay, negative 65.85 point,
So
yeah, 9, yeah, millivolts, great, perfect. Negative 65.9 millivolts. That's usually what the cell is at rest, actually, right? We're pretty close to minus 70 millivolts. So this is going to be a solid line. This is what we would probably measure with a voltmeter at minus 65.9 millivolts. Perfect. Okay, so what I want you to notice right away is this is about 9.5 times closer to the equilibrium potential for potassium than it is for sodium. Let me say it another way. Taking a look at this chart, can everybody see this chart? If this actual membrane voltage is minus 74 millivolts, right, what would you predict the total conductance to be? What would you predict for potassium and sodium? What do you think? Think about the Goldman-Hodgkin cast. If the resting membrane potential is sitting right on top of the equilibrium potential for potassium, what do you think the relative percentages would be for sodium and potassium? Wouldn't you? Yeah.
For potassium, it would be 1.
Yeah.
Sodium would be 0.
Perfect. So when we think about the conductances, if the actual membrane voltage is sitting right on top of the equilibrium potential, we could say 100% of the conductance is due to potassium. 0% is due to sodium. You all on the same page there? Okay, let's just pretend that the actual membrane voltage is sitting here at plus 89 millivolts. Wouldn't you agree that we could now say that 100% of the conductance is due to sodium and 0% is due to potassium? Right? Now, without even running any numbers, I'm going to ask you to predict what would be the membrane voltage if 50% of the conductance was due to sodium and 50% was due to potassium. Where do you think the membrane voltage, don't even run the numbers, where would you think that they would fall out? I think you know. What do you think?
Me?
Yeah.
Oh, I think it would be directly in the middle between sodium and potassium.
That's exactly right. It would be directly in the middle of these two. I would say just a little bit over 0 millivolts, right? Okay? So, again, Bernstein had it just right. If 90% of the conductance was due to potassium and only 10% was due to sodium, it would actually be very close to the equilibrium potential for potassium, right? Okay, so now I'm going to take it one step further. If here's our resting membrane potential, now, like with an action potential, let's just pretend that all of these sodium channels open up all of a sudden, and the relative conductances change. What's that going to do to the membrane voltage? It's going to pull the membrane voltage closer to the equilibrium potential for sodium, right? Now these voltage-gated sodium channels inactivate, and we turn on all these voltage-gated potassium channels. Potassium. What's that going to do? It's going to pull the membrane voltage closer to the equilibrium potential for potassium. And then when those potassium channels shut off, doesn't that look like an action potential? Okay? So that is exactly what Hodgkin and Huxley figured out, right? They figured out that the action potentials were due to the opening and closing of ion channels. No concentration gradient changes, just conductance changes, right? Just a few ions have to move across the membrane for it to pull the membrane voltage closer to the equilibrium potential and back down, okay? So you can already see that there are potassium channels that are open that are setting the resting membrane potential. I'll just fill in a few blanks. They're actually called leak potassium channels, and they set the resting membrane potential. They're technically called K2P channels, which are two-pore channels, but they're also known as leak channels. And then with action potentials, these are voltage-gated channels that open and close, that really are responsible for the action potential waveform in neurons and muscles. Okay? Don't worry, if this isn't resonating yet, we'll go over it again when we get to action potentials and talk about the difference between action and graded potentials. Right now, I can let you go. You can work on your problem sets if you want to leave early. This is all I had for today. On next Tuesday, we're actually going to jump right into passive, facilitated, and active transport. Okay? But I am here to answer any questions that you may have. This is a very difficult, I see this as very difficult concepts. And if you want to talk about it, I'll stay as long as you want before the class comes in.
Are we going to get problem set 2 on Tuesday then?
Yeah, no, I'm actually not going to pass out problem set number 2. We're going to move on Tuesday. So it's kind of your responsibility to, I gave you problem set, the part 1, but you'll have to download part 2 and do that on your own. And then both of them are due next Thursday, okay? And I'll return problem set number 1 on Tuesday. All right, good job. Woo-hoo. Hi.
Question. So is the value from this equation still theoretical, or is it like what it actually is?
Okay, so you're right, it's a calculated value, but you can assume that if I took a voltmeter and all of this was right,
Yeah.
this is a good line.
Okay.
So I would use a solid line for this case.
Okay.
Yeah, good question. Because you asked that other question last night.
Well, yeah, because if the other ones would be theoretical, you wouldn't actually measure it until you put in a meter to do that.
That's right.
But this one would be the actual value.
Right.
Okay.
So I would say with the equilibrium potentials, it's very rare that the actual membrane voltage is sitting right on top of equilibrium potentials.
Okay.
But when you use the flow conductance, that if I did use a voltmeter, it would be pretty close.
Okay.
Yeah.
All right.
Yep. Yeah, you're welcome. Thank you. Yeah, thank you very much. Hi.
I don't know if I should wait till the others are.
Oh, that's okay. Yeah.
I just have some questions.
Sure.
So my first